Picture the vast darkness of space, an endless void where stars flicker like distant campfires and galaxies swirl in silent majesty. But hidden within this breathtaking beauty lies a terrifying truth. The universe is not just a place of wonder. It's a battlefield of unimaginable forces where celestial monsters lurk in the shadows, capable of wiping out entire civilizations in the blink of an eye. What if I told you that some of these cosmic killers could be closer than we think? Lurking in the depths of space are objects so destructive, so utterly relentless, that they make black holes look tame. Today, we're diving into the 25 most dangerous objects in the universe, entities that defy our understanding of physics and challenge our very survival. Think about the sheer scale of the cosmos for a moment. We're floating on a tiny rock in an ocean of darkness, surrounded by forces beyond our control. Gamma-ray bursts, hypervelocity stars, rogue black holes, these aren't just science fiction. They're real and they're out there waiting. Some could tear apart planets with gravitational tsunamis. Others might unleash radiation storms so intense they'd sterilize entire solar systems without warning. And the scariest part, we've only begun to scratch the surface of what's lurking in the void. But this isn't just a story about doom and destruction. It's a journey into the heart of cosmic mystery, where the laws of physics twist into nightmarish shapes and the universe reveals its darkest secrets. By the end of this video, you'll see the night sky differently, not just as a canvas of stars, but as a realm where ancient, unstoppable forces wage eternal war. So buckle up. We're about to explore the most terrifying corners of existence, where danger doesn't just hide in the shadows, it thrives, ready to meet the monsters. Let's begin. Black holes are the ultimate cosmic vacuum cleaners, regions of space where gravity is so intense, not even light can escape their grasp. Picture standing at the edge of a bottomless pit where the very fabric of reality twists and stretches into oblivion. That's what happens near a black hole's event horizon, the point of no return. Cross it, and you're not just dying, you're being stretched into a single, atom-thin stream of matter in a process physicists call spaghettification. Take Sagittarius, a star, the supermassive black hole lurking at the center of our own Milky Way. It's 4 million times heavier than our Sun, silently dominating our galaxy's core. While it may seem distant, its gravitational influence shapes the orbits of every star nearby. If something or someone got too close, the tidal forces alone would rip them apart before they even reached the event horizon. But black holes aren't just cosmic destroyers, they're also time warpers. Near one, clocks tick slower than in the rest of the universe due to Einstein's theory of relativity. A few hours near a black hole could mean centuries passing elsewhere. And if that wasn't unsettling enough, some black holes spin at nearly the speed of light, dragging space itself into a vortex around them like water circling a drain. Then there's the real nightmare scenario: rogue black holes. These aren't anchored to any galaxy. They drift unseen through the cosmos, potentially wandering into a solar system unnoticed. By the time their gravitational pull starts bending starlight or tearing planets from their orbits, it's already too late. No warning, no escape, just an invisible predator swallowing everything in its path. Yet for all their terror, black holes also hold mysteries that could rewrite physics itself. Some theories suggest they might be gateways to other universes or tunnels through space-time. But until we crack those secrets, one thing's certain: in the presence of a black hole, the universe plays by rules far beyond our control. Spaghettification sounds like something out of a cartoon, but in reality, it's one of the most horrifying ways the universe can kill you. Imagine falling feet first toward a black hole. The pull of gravity on your legs would be exponentially stronger than the pull on your head, stretching your body like taffy into a single, thin strand of atoms. This isn't just theoretical, it's inevitable for anything crossing the event horizon. The difference in gravitational force, known as tidal forces, would shred molecules apart long before you reach the black hole's core. Even stars aren't spared. When one drifts too close, we've observed them being torn into luminous ribbons of plasma, swirling into oblivion in a process astronomers poetically call a tidal disruption event. But the warping of space isn't the only mind-bending effect black holes have. Time itself becomes distorted near these cosmic monsters. Thanks to Einstein's theory of general relativity, time slows down in extreme gravitational fields. Picture an astronaut orbiting just outside a black hole's event horizon. To them, minutes might pass normally, but back on Earth, decades could fly by. This isn't just science fiction. GPS satellites orbiting Earth have to account for tiny time distortions caused by our planet's gravity. Near a black hole, the effect is millions of times more extreme. The implications are staggering. If you could somehow hover near the edge of a black hole and watch the universe, you'd see stars being born, living out their lives and dying in fast forward. Galaxies would collide and merge in what felt like moments. Meanwhile, anyone observing you from afar would see you frozen in time, your image red shifted into invisibility as the black hole's gravity stretches light itself. What makes this even stranger is that black holes don't just warp time, they can twist it into knots. Some rotate at nearly the speed of light, dragging space-time around them like a whirlpool. Get too close and you'll be caught in this cosmic vortex, forced to move in the direction of the spin. There's no fighting it, no changing course. The universe itself is being pulled along for the ride. And here's the chilling part, we might not even see it coming. A rogue black hole could drift into our solar system undetected until its gravity starts bending light from distant stars. By then, planets would already be wobbling in their orbits, and Earth could be caught in an inescapable spiral. No explosion, no dramatic collision, just the silent, relentless pull of gravity rewriting the fate of everything in its path. Yet for all their destructive power, black holes also sculpt the universe in ways we're only beginning to understand. They might be the engines behind galaxy formation, the architects of cosmic structure. Some theories even suggest that black holes could be portals to other dimensions or universes, though crossing one would mean surviving forces beyond any material science. For now, they remain both destroyers and mysteries, reminding us that in the grand theater of the cosmos, the most terrifying forces are often the ones we understand the least. If black holes are the universe's ultimate predators, neutron stars are its unbreakable fortresses, cosmic remnants so dense they defy logic. Born from the violent death throes of massive stars in supernova explosions, these stellar corpses pack more mass than our sun into a sphere no wider than a city. The numbers alone are staggering. To grasp just how dense neutron stars are, picture scooping up a single teaspoon of their material. That tiny amount would weigh billions of tons here on Earth, as much as a mountain compressed into a speck. The crushing gravity on a neutron star's surface is so intense it warps the very rules of physics. Step onto one, if you somehow could, and you'd be flattened instantly into a thin film of atoms. Even light struggles to escape their pull, bending at bizarre angles as it tries to flee the star's gravitational grip. But gravity isn't the only deadly force at work here. Neutron stars boast magnetic fields trillions of times stronger than Earth's, powerful enough to rip apart molecules from thousands of miles away. Some neutron stars take this ferocity even further, becoming magnetars, a rare breed with magnetic fields 1,000 times stronger than their already terrifying cousins. These cosmic powerhouses emit bursts of X-rays and gamma rays so intense they can strip away a planet's atmosphere from halfway across the galaxy. In 2004, a magnetar 50,000 light-years away released a flare that briefly outshone the full moon despite being far beyond our solar system. If one of these eruptions happened closer, say within 10 light-years, it could devastate Earth's ozone layer, triggering mass extinctions. Then there are the pulsars, neutron stars spinning at dizzying speeds, some rotating hundreds of times per second. These cosmic lighthouses blast beams of radiation across space like deadly strobe lights, sweeping across the universe with eerie precision. Their pulses are so regular, astronomers initially mistook them for alien signals. But make no mistake, wandering too close to one would bombard you with enough radiation to vaporize a planet. What makes neutron stars especially unsettling is how quietly they lurk in the cosmos. Unlike black holes, they don't swallow light, they glow faintly, often hiding in plain sight. A rogue neutron star could drift into our solar system undetected, its gravity unsettling orbits long before we spotted it. And if it passed near Earth, tidal forces alone could trigger apocalyptic earthquakes, tsunamis, and volcanic eruptions, cracking our planet's crust like an eggshell. Yet for all their destructive potential, neutron stars are also cosmic gold mines, literally. The extreme pressures inside them forge heavy elements like gold, platinum, and uranium, which are flung into space during collisions, seeding the universe with the very materials that make up our jewelry and technology. They're destroyers and creators, proving once again that the deadliest forces in space often hold the keys to life itself. Magnetars take the nightmare fuel of neutron stars and crank it up to apocalyptic levels. These cosmic anomalies are neutron stars on steroids, their magnetic fields so ludicrously strong, they bend reality itself. We're talking about magnetic forces 1,000 trillion times more powerful than Earth's, enough to liquefy your body's atoms from the distance of the moon. If a magnetar appeared halfway between Earth and Mars, its magnetic field would erase every credit card on our planet in an instant, but financial chaos would be the least of our worries. The true horror lies in what scientists call starquakes. Picture the crust of a magnetar, a surface so dense, it's essentially a lattice of atomic nuclei packed shoulder to shoulder. When this unthinkably rigid crust fractures under magnetic stress, it unleashes energy equivalent to 100 billion atomic bombs. In 2004, a magnetar named SGR 1820 unleashed a gamma-ray blast so powerful, it actually compressed Earth's upper atmosphere from 50,000 light-years away. If that had happened within 10 light-years of us, the radiation would have triggered a mass extinction by destroying our ozone layer. What makes these events even scarier is their unpredictability. Unlike pulsars with their steady cosmic lighthouse beams, magnetars erupt without warning. Some emit repeated flares like cosmic tantrums, while others remain eerily quiet for decades before detonating in what astronomers term hyperflares. The most violent of these could outshine entire galaxies for a fraction of a second. The twisted physics gets even stranger when you consider how these monsters warp space-time itself. A magnetar's magnetic field is so intense, it actually distorts the quantum vacuum around it, the very fabric of empty space. Photons traveling near one get bent into bizarre loops, creating optical illusions that would make Einstein dizzy. Some theories suggest their fields might even spontaneously generate matter from pure energy, sparking miniature Big Bangs in their immediate vicinity. Yet for all their destructive potential, magnetars might hold clues to the universe's greatest mysteries. Their extreme conditions mimic what physicists suspect existed microseconds after the Big Bang. By studying them, we're essentially peering back to the birth of reality itself. That cosmic irony defines these lethal marvels. They are both destroyers of worlds and keys to understanding existence. One day, that knowledge might save us. Until then, we'd better hope none of them decide to sneeze in our galactic neighborhood. Gamma-ray bursts are the universe's ultimate cosmic fireworks, spectacular, devastating, and over in the blink of an eye. These fleeting eruptions of energy pack more power than anything else in existence, unleashing in mere seconds what our sun will radiate over its entire 10 billion-year lifespan. Imagine a single event outshining every star in the observable universe combined, but only for a heartbeat. That's the terrifying scale of a gamma-ray burst. These explosions come in two deadly flavors. Short gamma-ray bursts last less than 2 seconds and are thought to be caused by colliding neutron stars, cosmic mergers so violent they ripple space-time itself. The longer bursts, stretching minutes, occur when massive stars collapse into black holes, their death throes firing twin jets of radiation at near light speed. Either variety would spell doom for any nearby planet. The real horror lies in what happens if one of these beams points directly at Earth. A gamma-ray burst within 6,000 light-years would bathe our planet in enough high-energy radiation to strip the ozone layer, leaving life exposed to the sun's full fury. The skies would glow blindingly bright for seconds before the aftermath began, a cascade of acid rain, global cooling, and DNA-shredding ultraviolet light penetrating every corner of the planet. Scientists believe such an event might explain some of Earth's past mass extinctions, like the Ordovician die-off 450 million years ago that erased 85% of marine species. What makes gamma-ray bursts especially unnerving is their unpredictability. Unlike supernova, which give days or weeks of warning as a star brightens, these bursts arrive without preamble. One moment the sky is normal, the next it's saturated with enough gamma rays to trigger radiation alarms worldwide. Astronomers detected a burst in 2019 so powerful. Its light traveled 7 billion years to reach us, yet for a few seconds it was visible to the naked eye despite being halfway across the observable universe. The silver lining, these cataclysms are rare in our galactic neighborhood. The Milky Way structure and our position far from its crowded center make a direct hit unlikely. But wander too close to a galaxy undergoing a starburst phase where stars form and die at frenzied rates, and the odds climb dramatically. Some researchers speculate that gamma-ray bursts could be the universe's way of resetting the clock, sterilizing regions of space to make way for new cosmic experiments. Yet, even as potential harbingers of annihilation, these bursts serve as cosmic lighthouses. Their light carries clues about the early universe, helping astronomers map the distribution of matter across billions of light-years. In death, they illuminate the very fabric of existence, proving once again that the universe's most destructive forces often hold its deepest secrets. GRB 080319b wasn't just another gamma-ray burst, it was a wake-up call. Detected in March 2008, this cosmic explosion erupted from a galaxy 7.5 billion light-years away, yet for 30 seconds it was visible to the naked eye here on Earth as a faint pinprick of light. That's like spotting a candle on the moon. The energy released was so incomprehensibly vast, it outshone the entire observable universe in gamma rays for half a minute. Now imagine that same burst occurring not billions of light-years distant, but in our galactic backyard. The consequences would be nothing short of apocalyptic. A gamma-ray burst within 6,000 light-years, well within the Milky Way, would deliver a 1-2 punch of annihilation. First, the initial blast would bombard our atmosphere with enough high-energy photons to rip apart nitrogen and oxygen molecules, triggering a chain reaction that destroys the ozone layer within weeks. Without this protective shield, Earth's surface would be bathed in lethal ultraviolet radiation from the sun, turning daylight into a carcinogenic flood. Photosynthesis would collapse, unraveling food chains from the ground up. Crops would wither, plankton, the foundation of oceanic life, would die off, and within months, starvation would eclipse radiation as the primary killer. But the horror doesn't stop there. The gamma rays would also ionize the atmosphere, generating nitrogen oxides that cloaking the planet in a smog capable of blocking sunlight for years. Global temperatures would plummet, mimicking a nuclear winter. Rainfall patterns would shift violently, turning fertile regions into deserts and triggering mass migrations. Scientists studying the fossil record point to the Ordovician extinction 450 million years ago as a possible victim of such an event. a sudden die-off where marine species vanished almost overnight, their ecosystems obliterated by what looks eerily like radiation poisoning in the geological record. What makes GRB 080319b particularly chilling is its naked eye visibility. Most bursts are only detectable by satellites, but this one crossed a terrifying threshold of brightness. Had it been 1,000 times closer, still cosmically distant, it would have lit up Earth's sky like a second sun for days, its afterglow frying satellites and frying electronics worldwide. The EMP-like effects alone could knock out power grids, crippling civilization before the ecological dominoes even began to fall. Yet amidst the doom, there's a strange cosmic irony. Gamma-ray bursts might be the universe's way of pruning life to make room for new experiments. Their lethal radiation could sterilize entire galaxies, but in doing so, they might also distribute heavy elements forged in stellar deaths, the very atoms that later coalesce into planets and eventually life. We could owe our existence to ancient bursts that cleared the stage for Earth's evolution. The same force that extinguishes worlds might also seed them, a reminder that in the grand cosmic cycle, destruction and creation are two sides of the same coin. Rogue planets are the universe's silent nomads, worlds torn from their star systems and cast adrift in the endless dark. Picture an Earth-sized object, frozen and airless, hurtling through space at hundreds of thousands of miles per hour with no sun to warm it, no light to illuminate its surface. These orphaned worlds aren't rare. Astronomers estimate billions might be wandering the Milky Way alone, invisible to telescopes until they drift close enough to betray their presence. The danger lies in their unpredictability. A rogue planet passing through our solar system wouldn't need to collide with Earth to spell disaster. Its gravity alone could yank asteroids from the belt, sending them careening inward. Neptune's orbit could be perturbed, destabilizing the delicate gravitational balance that keeps our cosmic neighborhood stable. Even a distant flyby might nudge Earth into a slightly different orbit, enough to trigger ice ages or scorching temperature swings over centuries. But a direct impact, that's true cosmic horror. A Mars-sized rogue planet striking Earth would release energy equivalent to trillions of nuclear bombs. The collision would vaporize oceans, shatter continents, and hurl enough debris into orbit to blot out the sun for millennia. The last time something similar happened, 4.5 billion years ago, the resulting debris formed our moon. Another strike wouldn't create, it would obliterate. What makes rogue planets especially chilling is how hard they are to spot. Unlike stars, they emit almost no light. Some might still glow faintly from radioactive decay in their cores, but most are colder than Pluto. By the time one's gravity distorts the light of background stars, our best detection method, it could already be too close to evade. Yet there's a haunting beauty to these wanderers. Some might harbor subsurface oceans kept liquid by tidal friction or geothermal heat, making them dark, frozen ark ships for microbial life ejected from their home systems. Others could be rich in exotic ices or metals, valuable beyond measure if we ever develop the technology to mine them. But for now, they remain both a threat and a mystery, ghostly reminders that the universe doesn't need stars or black holes to produce celestial monsters. Sometimes all it takes is a world torn from its roots, set loose to wander the cosmic void until gravity decides its fate. Hypervelocity stars are the universe's runaway bullet, stellar projectiles racing through the void at speeds that defy imagination. These aren't your average stars drifting lazily through galactic currents. They're cosmic outlaws ejected from their homes at over 1 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. The forces behind their exile, gravitational slingshots from supermassive black holes or violent galactic collisions that fling stars like pinballs across the cosmos. Take the infamous star known as S5HVS1, clocked at nearly 1.6 million miles per hour. It's moving so fast, it's not just escaping its home galaxy, it's breaking free from the gravitational pull of the entire local group of galaxies. At that speed, it could traverse the length of our solar system in less than a day. Now imagine such a star barreling through a populated region of space. The gravitational chaos alone would be catastrophic. Planets orbiting nearby stars could be yanked from their orbits, comets hurled into interstellar space, and asteroid belts stirred into a frenzy of collisions. But the real danger lies in what these stellar speedsters carry with them. Some hypervelocity stars are massive, short-lived giants destined to explode as supernova. A star like this passing even a light year from Earth would be like a ticking time bomb. When it detonates, the resulting shockwave and radiation could sterilize our planet. In 2007, astronomers discovered a hypervelocity star racing toward the edge of the Milky Way at speeds that suggest it was launched by the supermassive black hole at our galaxy's core. Had it been aimed inward instead of outward, it could have become a looming doomsday scenario for any system in its path. Then there's the rogues gallery of hypervelocity binaries, pairs of stars flung together at breakneck speeds. If one of these duos included a white dwarf, the gravitational dance could lead to a Type Ia supernova, the same kind of stellar explosion used to measure cosmic distances. Picture a supernova detonating not in some distant galaxy, but on our galactic doorstep, its light outshining the full moon and its radiation bathing nearby planets in lethal X-rays. What makes these stars truly unsettling is how powerless we'd be against them. Unlike asteroids or comets, we can't deflect something with the mass of a star. By the time telescopes spotted one on a collision course with our solar system, there'd be no time to act. The only warning might be a gradual distortion in the orbits of outer planets, a subtle tug before the storm. Yet hypervelocity stars aren't just agents of chaos. They're also cosmic archaeologists. Their trajectories trace back to violent events millions of years ago, offering clues about the workings of supermassive black holes and the mergers of ancient galaxies. Some might even carry planetary hitchhikers, frozen worlds torn from their homes, now adrift between the stars. These orphaned planets could number in the trillions, a hidden population of dark travelers silently crisscrossing the galaxy. So while hypervelocity stars might be rare, their potential for destruction is matched only by their scientific value. They remind us that the universe is anything but static. It's a roiling sea of motion, where even the stars themselves can become weapons flung across the void. The next time you look up at the night sky, consider this. Somewhere out there, a star is racing toward oblivion at unimaginable speed, and we're lucky it's not headed our way. Quasars are the universe's ultimate power plants, beacons of destruction so bright they outshine entire galaxies. Imagine a supermassive black hole, millions of times heavier than our sun, gorging on stars, gas, and dust with insatiable hunger. But unlike their quieter cousins, quasars don't just consume matter silently. They transform it into pure energy, firing jets of radiation so intense they can sterilize planets thousands of light years away. These aren't just celestial objects, they're cosmic blowtorches burning at the edge of spacetime itself. At the heart of every quasar lies a supermassive black hole, but with a terrifying twist. As material spirals into the black hole's accretion disk, friction heats it to millions of degrees, creating a swirling maelstrom of plasma brighter than a trillion stars. Some of this superheated matter doesn't fall in. It's hurled back into space at nearly light speed, focused into narrow beams that stretch for hundreds of thousands of light years. These jets are so powerful they punch through entire galaxies, ionizing everything in their path. If one were pointed at Earth, the radiation would strip our atmosphere like sandblasting paint off metal. The numbers defy comprehension. The brightest quasars emit more energy in a single second than our sun will in its entire 10 billion-year lifespan. Their light, traveling billions of years to reach us, acts as a time capsule from the early universe when quasars were far more common and galaxies collided in violent bursts of creation. Back then, the night sky of any nearby planet would have been lit by these cosmic lighthouses, their glare drowning out all but the closest stars. What makes quasars especially unnerving is their ability to reshape entire galaxies. Their jets don't just fry planets, they can halt star formation by blasting away the gas clouds needed to birth new suns. Astronomers have observed galaxies where quasars effectively quenched their own growth, leaving behind dead husks of aging stars. It's a cosmic catch-22. The very engine that powers a quasar eventually destroys the fuel supply that sustains it. Yet for all their destructive potential, quasars also hold clues to the universe's largest structures. Their light bends around intervening galaxies, revealing the presence of dark matter. Their spectra act as fingerprints, showing the composition of gas clouds billions of years ago. Some researchers even speculate that quasars could be the birth cries of supermassive black holes, growing rapidly in the densest regions of the early cosmos. The closest known quasar, 3C273, lies 2.5 billion light-years away, comfortably distant. But during the universe's chaotic youth, when quasars ruled the cosmos, Earth's ancestors were single-celled organisms dodging extinction events in a primordial ocean. Had one ignited nearby back then, life might never have gotten its chance. Today, we study these monsters with awe and relief, grateful they're distant enough to observe but not close enough to erase us. In the grand cosmic lottery, we won the jackpot, a quiet corner where the universe's most violent powerhouses are brilliant, but safely far away. Dark matter is the universe's greatest unsolved riddle, an invisible force shaping the cosmos while remaining utterly elusive. Think of it as the scaffolding behind everything we see. Galaxies, stars, even the largest structures in existence are held together by its gravitational glue. Yet despite making up 27% of the universe's total mass, dark matter refuses to interact with light, leaving telescopes blind to its presence. We only know it's there because without it, galaxies would spin apart like shattered glass. The danger lies in its unpredictability. Unlike black holes or neutron stars, dark matter doesn't announce itself with radiation or violent collisions. It's a silent puppeteer tugging at the cosmos from the shadows. Some theories suggest dark matter could clump into massive, diffuse blobs, drifting between galaxies, structures with enough gravity to yank stars off course or distort entire solar systems. If one passed through ours, the subtle gravitational tugs could send planets spiraling into erratic orbits, turning Earth's stable path around the Sun into a chaotic roller coaster. Winters might stretch for decades, summers vanish entirely, and the delicate balance keeping life alive would unravel. Then there's the nightmare scenario, dark matter annihilation. Certain models propose that when dark matter particles collide, they might release bursts of gamma rays or other lethal radiation. Normally, these interactions are rare, but if a dense knot of dark matter settled near Earth, the resulting particle decays could bathe our planet in a slow, invisible poison. No fiery explosions, no dramatic impacts, just a gradual increase in cancer rates, mutations, and ecosystem collapse as background radiation climbs to intolerable levels. What makes dark matter truly unsettling is how little we know. It could be made of weakly interacting massive particles or actions, hypothetical particles lighter than electrons. Some scientists even speculate it might consist of primordial black holes formed in the universe's first second. Until we crack its identity, we're essentially living in a house haunted by a ghost we can't see, hear, or touch, one that could rearrange the furniture at any moment. Yet for all its mystery, dark matter might also be the universe's saving grace. Without it, galaxies wouldn't have formed in the early cosmos, leaving space an empty sea of hydrogen. Its gravitational pull continues to shape the cosmic web, guiding the birth of new stars and planets. One day, understanding dark matter could unlock everything from warp drive to cosmic archaeology, revealing secrets about the universe's infancy we can't yet fathom. For now, it remains both architect and enigma, the unseen hand that built the cosmos, capable of unmaking it just as silently. Every time you look at the night sky, remember, what's visible is just the tip of the iceberg. The real action happens in the dark. Antimatter is the universe's ultimate self-destruct button, a mirror image of ordinary matter with one terrifying difference. Every particle of antimatter carries the opposite charge of its normal counterpart. When the two meet, they annihilate each other in a flash of pure energy, converting their combined mass into gamma rays with 100% efficiency. A single gram of antimatter reacting with matter would release the explosive power of 43,000 tons of TNT, dwarfing the atomic bombs dropped on Hiroshima and Nagasaki. Surprisingly, antimatter isn't just science fiction. It's created naturally in small quantities across the cosmos. Lightning strikes on Earth produce fleeting bursts of positrons, antimatter electrons, while cosmic rays from deep space constantly rain down antiprotons onto our atmosphere. Even bananas emit antimatter. The potassium-40 in them decays, spitting out a positron every 75 minutes. But these are trivial amounts. The real danger lies in concentrated antimatter lurking in space. Picture an antimatter asteroid, a chunk of rock forged in some exotic astrophysical event, composed entirely of antiprotons and antineutrons instead of ordinary atoms. If one collided with Earth, the resulting annihilation would unleash energy on par with the dinosaur-killing Chicxulub impact, but with a horrifying twist. Instead of just excavating a crater, the antimatter would react explosively with our planet's surface material, triggering a chain reaction that could vaporize entire continents in minutes. The gamma-ray flash alone would ionize the atmosphere, while the shockwave would circle the globe multiple times, scouring the land clean. What makes antimatter especially unsettling is how stealthy it could be. Until it interacts with normal matter, it's indistinguishable from regular asteroids in telescopes. A 1-kilometer-wide antimatter rock could be days away from impact before its anomalous radiation signature gave it away. And unlike nuclear weapons, there's no way to disarm. Antimatter contact equals instant annihilation. Yet for all its destructive potential, antimatter also holds promise. It's the most energy-dense fuel known to physics, capable of propelling starships to relativistic speeds if we could produce and store it safely. CERN creates nanograms of antimatter annually, trapping it in magnetic bottles to study its properties. One day, mastering antimatter might unlock interstellar travel, or if weaponized, become the ultimate doomsday device. The universe seems to favor matter overwhelmingly, with antimatter vanishingly rare. But that imbalance itself is a mystery. According to physics, the Big Bang should have created equal amounts of both, leading to total annihilation. The fact that we exist means something tipped the scales. Understanding antimatter isn't just about fear. It's about solving one of cosmology's greatest riddles: why there's anything left at all. Vacuum decay is the universe's ultimate reset button, a hypothetical disaster so absolute it wouldn't just destroy Earth or the Milky Way, but erase the fundamental laws of physics across the entire cosmos. Picture a single quantum fluctuation, a random blip in the fabric of reality, that punches through the fragile stability of our universe like a needle popping a balloon. In an instant, a bubble of true vacuum forms, expanding outward at the speed of light, rewriting existence itself as it spreads. One moment, the universe operates under the rules we know: gravity, electromagnetism, the nuclear forces holding atoms together. The next, everything we consider reality could unravel in a wave of total transformation. The concept hinges on a terrifying possibility that the universe isn't in its most stable state. Think of it like a marble resting in a divot on a hillside. It seems stable until something nudges it, sending it tumbling downhill to a lower energy state. Our cosmos might be similarly perched, with the quantum fields governing physics sitting in a false vacuum, that could, at any moment, collapse into a more stable configuration. The trigger could be as random as a high-energy particle collision or as deliberate as an experiment in a super collider. Once the process starts, there's no stopping it. The bubble's boundary would race outward faster than any signal could warn us, annihilating not just matter, but the very forces that bind it. Protons might disintegrate. Electrons cease to exist. Even space-time itself could reconfigure, rendering concepts like distance and time meaningless. The worst part, we wouldn't see it coming. The wavefront would move at light speed, giving zero warning before it hit. 1 nanosecond, you're sipping coffee, the next the coffee, and the very molecules composing your hand no longer function under recognizable physics. This isn't just theoretical doom-mongering. The math checks out. Quantum field theory allows for such a transition, and the Higgs boson's mass suggests our vacuum might indeed be metastable, like a match balanced on its head. In 2012, calculations at the University of Southern Denmark estimated the Higgs field's current state is precarious, not quite unstable, but uncomfortably close. A sufficiently energetic event, like a black hole merger or a cosmic strings collapse, might provide the nudge needed to tip the balance. Yet vacuum decay isn't all grim speculation. It hints at deeper truths about the universe's origins. If our vacuum is metastable, others might exist parallel universes with radically different physics, forever separated by walls of destructive phase transitions. Some theories even suggest our own universe could be the aftermath of an earlier vacuum decay event, a cosmic accident that spawned a pocket of stability amid the chaos. While the odds of spontaneous vacuum decay are astronomically low, likely lower than the heat death of the universe, it remains a humbling reminder of how fragile reality might be. All it takes is one quantum sneeze in the right place, and everything from quasars to quantum foam could be rewritten in an instant. The universe doesn't need malice to end life as we know it. Sometimes all it takes is physics deciding it's time for an upgrade. White holes are the universe's unhinged fire hydrants, theoretical opposites of black holes where gravity loses its grip and matter erupts uncontrollably into space. If black holes are cosmic vacuum cleaners, white holes are their malfunctioning counterparts, violently spitting out everything they've ever swallowed. Imagine a singularity that refuses to keep anything down, a gravitational regurgitation so violent it could light up galaxies with the energy of 1,000 supernovae. These bizarre objects exist only as mathematical possibilities in Einstein's equations, but if they're real, they'd rewrite the rules of cosmic destruction. Unlike their dark cousins, white holes can't be entered, only escaped. Their event horizons act like one-way doors swinging outward, hurling particles and radiation at near light speed. Picture a cosmic geyser blasting a jet of superheated plasma millions of miles into space, frying anything in its path. The energy output would dwarf quasars, making white holes some of the brightest objects in existence if they lasted long enough to be seen. Theoretical models suggest they might be extremely unstable, collapsing into black holes or evaporating within moments of forming. But in that brief window, their fury would be unmatched. The scariest scenario, a white hole forming near a populated region of space. Its sudden matter discharge would create a shockwave of radiation and high-energy particles, sterilizing planets hundreds of light-years away. The outburst could also destabilize local spacetime, warping orbits and triggering cascades of collisions in nearby star systems. Some physicists speculate that gamma-ray bursts, those universe-spanning explosions we discussed earlier, might actually be white holes briefly flickering into existence before vanishing back into the cosmic void. Yet white holes aren't just engines of chaos. They might also hold clues to the birth of universes. One radical theory suggests our own Big Bang could have been the eruption of a white hole in a parent universe, spewing out the material that became our cosmos. Others propose they're the other end of black hole tunnels, connecting distant points in spacetime through wormholes. Of course, passing through one would still be fatal. Tidal forces would shred anything attempting the journey. But the idea tantalizes physicists searching for unified theories of gravity and quantum mechanics. For now, white holes remain firmly in the realm of speculation. No telescope has ever detected one, and their existence would require rewriting parts of general relativity. But that's the beauty of cosmic mysteries. They push us to question the fabric of reality itself. Whether they're out there or not, white holes remind us that the universe has a flair for the dramatic, capable of conjuring unthinkable violence from the cold equations scribbled in a physicist's notebook. Kilinovae are the universe's ultimate alchemists. Cosmic collisions so violent, they forge gold in the heart of destruction. When two neutron stars spiral toward each other in a lethal dance, their merger unleashes energies beyond comprehension, ripping apart the very fabric of spacetime. These cataclysms don't just create gravitational waves, they spew out enough heavy elements to seed entire galaxies with the building blocks of planets and life. That ring on your finger, the gold in it was likely forged in a kilonova billions of years ago, ejected into space before our solar system even existed. But the beauty of creation comes with a price. A kilonova's aftermath is a nightmare for any nearby world. The initial collision releases a gamma-ray burst, one of the most powerful explosions in existence, capable of sterilizing planets thousands of light-years away. Then comes the shockwave of gravitational ripples, distorting spacetime itself as it propagates outward. In 2017, scientists detected gravitational waves from a kilonova 130 million light-years away, marking the first time humans witnessed gold being forged in real time. The event, dubbed GW170817, was so bright it briefly outshone its host galaxy. The radiation doesn't stop there. Kilonovae blast out a lethal cocktail of X-rays, ultraviolet light, and high-energy particles called cosmic rays. These subatomic bullets travel near light speed, penetrating atmospheres and mutating DNA. A nearby kilonova could trigger mass extinctions, not through immediate fire, but through a slow poisoning of ecosystems, a silent apocalypse unfolding over decades. And if that weren't enough, the ejected debris from the collision expands at a fraction of light speed, a shimmering cloud of radioactive isotopes that glows for weeks. Any planet caught in this expanding wave would be bathed in a lingering death fog, its surface scoured by radiation storms worse than a nuclear winter. What makes kilonovae uniquely terrifying is their unpredictability. Unlike supernova, which give some warning as stars destabilize, neutron star collisions happen suddenly, often between dead stars too faint to monitor closely. The Milky Way hosts billions of neutron stars, and while most are solitary, some exist in binary pairs destined to merge. If one such pair lurked within a few hundred light-years of Earth, we might not know until the gamma-ray flash illuminated our atmosphere, a split-second warning before the cascading effects began. Yet these cataclysms are also cosmic life-givers. The gold, platinum, and uranium ejected by kilonovae eventually coalesce into new generations of stars and planets, enriching the universe with elements vital for technology and life. Our very existence is tied to these violent events, a reminder that destruction and creation are two sides of the same coin. The same collision that could erase civilizations also plants the seeds for their rebirth. Kilonovae embody the universe's relentless duality, beautiful and brutal, creative and catastrophic. They're proof that even in the darkest corners of space, destruction carries the spark of something new, a cycle as old as time itself. So the next time you admire a piece of jewelry or ponder the origins of Earth's heavy metals, remember, they were born in a firestorm of annihilation, a testament to the universe's endless capacity for reinvention. Pulsars are nature's perfect particle accelerators, spinning remnants of dead stars so precise they rival atomic clocks. But beneath their hypnotic rhythm lies a lethal secret. These cosmic lighthouses don't just pulse with light. They fire focused beams of radiation so intense they could strip a planet's atmosphere clean off in mere decades. Picture a celestial blowtorch sweeping through space, its deadly beam slicing across solar systems with surgical precision. If Earth strayed into the crosshairs of one of these beams, the consequences would make a supernova look tame by comparison. Take the pulsar Psr 357+56 discovered in the constellation Gemini. It rotates a staggering 716 times per second, whipping its magnetic poles around so fast, it generates beams of X-rays and gamma rays powerful enough to ionize atoms from light years away. These aren't harmless radio waves like the ones pulsars were first discovered with their death rays in every sense of the word. A planet caught in the direct path would face a relentless assault of high-energy particles, eroding its atmosphere molecule by molecule. Ozone would vanish first, exposing the surface to lethal ultraviolet radiation. Next, nitrogen and oxygen would be torn apart, their atoms stripped of electrons until the very air became electrically charged, a recipe for global firestorms and acid rain on a biblical scale. The scariest part, pulsars don't announce their threat with a bright explosion or visible flare. Their beams are narrow, often just a few degrees wide, meaning a solar system could drift into the kill zone without warning. Astronomers call this a pulsar wind nebula, a euphemism for the hellish environment created when these beams collide with interstellar gas. The Crab Nebula, powered by the pulsar at its core, churns out enough energy to light up the entire electromagnetic spectrum, from radio waves to gamma rays. If Earth orbited within even 100 light-years of such a beast, the constant radiation barrage would make the surface uninhabitable within centuries. What makes pulsars uniquely terrifying is their longevity. Unlike supernova, which fade within years, pulsars can keep firing their beams for millions of years. Some, like the so-called Black Widow pulsars, even use their radiation to slowly vaporize companion stars, a gruesome preview of what might happen to any planet unfortunate enough to share their space. And while the odds of a pulsar beam directly hitting Earth are astronomically low, the universe is vast enough that somewhere, right now, a world might be suffering exactly that fate. Yet pulsars aren't just instruments of destruction. Their precision makes them invaluable cosmic tools. The timing of their pulses has helped astronomers map the Milky Way's magnetic field and even test Einstein's theory of relativity. Some scientists speculate that advanced civilizations might use pulsars as interstellar navigation beacons, assuming they could withstand the radiation long enough to get close. For now, these stellar zombies remain both a marvel and a menace. Their beams pierce the darkness with clockwork regularity, a reminder that in the cosmic game of chance, even the most predictable objects can harbor unimaginable danger. The next time you hear about the steady tick of a pulsar, remember, that's not just a heartbeat from a dead star. It's the metronome of a potential doomsday clock counting down in the void. Hidden at the core of our Milky Way, a sleeping giant occasionally wakes in fits of unimaginable violence. Galactic superwaves, tsunamis of high-energy cosmic rays, erupt from the supermassive black hole at our galaxy's center, flooding the cosmos with enough radiation to rewrite the fate of civilizations. These aren't gentle ripples, they're shockwaves carrying the energy of 100 million supernovae, capable of stripping planets of their atmospheres and bombarding life with mutation-inducing particles. And Earth isn't as safe from them as we'd like to believe. Evidence from ice cores and ancient tree rings suggests our planet has weathered these storms before. Around 12,000 years ago, during an event called the Younger Dryas, Earth suddenly plunged back into Ice Age conditions while megafauna like woolly mammoths vanished. Scientists analyzing layers of radioactive isotopes found spikes of beryllium-10 and chlorine-36, telltale fingerprints of intense cosmic ray bombardment. The leading theory, a galactic superwave likely triggered by an outburst from Sagittarius, a star, our galaxy's central black hole. The mechanics behind these eruptions are terrifyingly simple. When the black hole devours a massive cloud of gas or a star, it doesn't just swallow matter quietly. The infalling material forms a swirling accretion disk hotter than a million suns, launching jets of particles accelerated to nearly light speed. These particles, mostly protons, crash into interstellar gas, creating secondary cascades of deadly radiation that propagate outward like a shock wave through the galaxy. Unlike gamma-ray bursts, which are focused beams, superwaves spread in all directions, giving no safe harbor to planets in their path. A direct hit today would unleash slow-motion devastation. Initially, the surge of cosmic rays would overwhelm Earth's magnetic field, allowing particles to penetrate deep into the atmosphere. Within weeks, radiation levels at the surface could triple, increasing cancer risks and damaging DNA across all species. The real nightmare begins when these particles collide with nitrogen and oxygen in the air, generating showers of secondary radiation like muon subatomic bullets that slice through concrete and flesh alike. Air travel would become lethal, surface water unsafe, and entire ecosystems would collapse under the genetic damage. But the worst effects might be climatological. Cosmic rays ionize the atmosphere, seeding cloud formation that could plunge Earth into a decades-long winter. Agriculture would fail as growing seasons vanished, triggering global famine. And unlike asteroid impacts or supervolcanoes, there'd be no geological evidence until it was too late, just a gradually darkening sky and a silent uptick in radiation sickness cases worldwide. What makes galactic superwaves uniquely unsettling is their inevitability. Sagittarius, a star, erupts roughly every few thousand years, and we're statistically overdue for another. The only silver lining: distance buys us time. At 26,000 light-years from the galactic center, we'd have millennia to prepare if we spotted a wave coming, assuming our telescopes could distinguish its signature from background cosmic noise. Yet these apocalyptic events might also hold the key to life's origins. Some researchers speculate that past superwaves could have delivered the heavy elements and radiation bursts necessary to jumpstart early genetic molecules. The same force that threatens complex life may have set the stage for its emergence, a paradox as old as the cosmos itself. So while we monitor the galaxy's heart for signs of awakening, we're left to ponder our fragile place in a universe where creation and destruction share the same cosmic address. Most black holes stay anchored at the centers of galaxies, but the universe has a way of creating cosmic renegades, rogue black holes that wander the void like gravitational ghosts. These invisible predators don't announce their presence with glowing accretion disks or violent jets. They drift through space unseen, their gravity the only clue to their passing. And if one decided to pay our solar system a visit, we might not realize it until entire planets started veering off course. Take the case of a black hole 10 times the mass of our Sun, relatively small by cosmic standards. At just 1 light-year away, its gravity would already be yanking comets from the Oort cloud, sending icy bodies careening toward the inner solar system. By the time it reached Pluto's orbit, the distortions would be unmistakable. Outer planets would wobble in their paths like marbles on a tilted table, their orbits warping under the black hole's relentless pull. Earth's orbit might stretch into an elongated oval, turning summers into scorching droughts and winters into deep freezes. Tidal forces could trigger volcanic eruptions and earthquakes as our planet's crust flexed under the strain. The real nightmare begins if the black hole passes through the solar system's plane. Like a bowling ball rolling across a trampoline, its gravity would send planets and asteroids ricocheting in chaotic new trajectories. Jupiter might be flung outward, abandoning its role as Earth's protective shield against incoming comets. Mars could spiral into the Sun or worse, collide with us. Even a near miss would leave the solar system permanently unbalanced, a celestial crime seen with gravity as the silent killer. What makes rogue black holes especially terrifying is how they form. Some get ejected during galaxy collisions, slingshotted away by the gravitational dance of merging supermassive black holes. Others might be primordial leftover from the Big Bang itself, lurking in the darkness for billions of years. And because they're not actively feeding, they emit no telltale X-rays or gamma rays. The only way to spot one is by observing its gravitational lensing effect, the way it bends light from distant stars like a funhouse mirror. By then, it could already be too close to escape, yet these cosmic drifters aren't just agents of chaos. They might hold clues to the universe's most profound mysteries. Some theories suggest rogue black holes could be made of dark matter, their gravity shaping galaxies from the shadows. Others propose they're the seeds of future supermassive black holes waiting to collide and grow in the cosmic deep. One thing's certain, in a galaxy teeming with visible threats, supernova, gamma-ray bursts, neutron stars, it's the invisible ones that might be the most dangerous. A rogue black hole doesn't need to consume Earth to doom us. Sometimes all it takes is a gentle gravitational nudge at the wrong place, the wrong time, rewriting the solar system's fate in the dark. The very laws of physics that hold our universe together might be sitting on a knife's edge, a precarious balance that could topple at any moment. This isn't science fiction. It's a legitimate possibility rooted in quantum field theory called false vacuum collapse. Picture reality as a valley surrounded by mountains, with our universe sitting comfortably at the bottom. But what if that valley isn't the lowest point? What if there's a deeper chasm hidden beyond the peaks, a more stable state of existence that our cosmos could abruptly tumble into without warning? The nightmare scenario goes like this. Somewhere in the vastness of space, a random quantum fluctuation could punch through the fragile barrier separating our current vacuum state from a lower energy one. Think of it like poking a pin through a balloon. In an instant, a bubble of this true vacuum would form, expanding outward at the speed of light, rewriting the fundamental forces of nature as it spreads. Inside this bubble, the rules we take for granted, gravity, electromagnetism, even the nuclear forces binding atoms, would cease to function as we know them. Protons might disintegrate, electrons could vanish, space and time themselves might reconfigure into something unrecognizable. The terrifying part, we'd have no warning. The boundary of this bubble moves at light speed, meaning the first sign of disaster would be its arrival. One moment you're sipping coffee, the next the coffee and the very molecules composing your hand no longer obey the physics that make life possible. Entire galaxies would blink out of existence in real time, erased not by fire or ice, but by a silent reconfiguration of reality's blueprints. This isn't just wild speculation. The math checks out. The discovery of the Higgs boson in 2012 revealed that the Higgs field, the invisible energy field giving particles their mass, might not be in its most stable state. Calculations suggest our universe could be metastable, like a match balanced on its head. It's lasted billions of years, sure, but all it takes is one quantum nudge in the right place to send everything tumbling. That nudge could come from anything: a high-energy particle collision in a super collider, the decay of a strangelet, or even a random quantum burp in deep space. Yet, even as we grapple with this existential threat, false vacuum collapse hints at something profound. If our universe is metastable, others might exist beyond it, cosmic bubbles with entirely different physics, forever separated by walls of annihilation. Some theories even propose that our own Big Bang was the result of a false vacuum collapse in a parent universe, meaning we're already living in the aftermath of one cosmic reset. For now, the odds of spontaneous collapse are vanishingly small, likely lower than the heat death of the universe. But the mere possibility forces us to confront a humbling truth. Reality itself might be fleeting, a temporary configuration in an infinite sea of potential existences. The laws we rely on, the constants we measure, even the fabric of space-time, all of it could be rewritten in an instant without fanfare or farewell. In the grand scheme of things, we're not just living in a universe. We're living on borrowed time. Cosmic strings are the universe's most razor-sharp enigmas, hypothetical cracks in space-time so thin they'd slice through atoms like a hot knife through butter, yet dense enough to warp the fabric of reality itself. Picture a defect in the cosmic tapestry, a one-dimensional filament thinner than a proton but stretching across the entire observable universe, left over from the first chaotic moments after the Big Bang. These aren't just theoretical oddities. If they exist, they'd wield power beyond anything else in nature. A single cosmic string passing through Earth would cleave our planet in half with surgical precision, not through brute force, but by warping space-time so severely that 2 points on opposite sides of the string would suddenly find themselves light years apart. The physics behind these nightmares is rooted in the universe's infancy. As the cosmos cooled in the first fractions of a second after the Big Bang, phase transitions rippled through space-time like cracks forming in ice. Some theories suggest these cracks didn't heal. They froze into place, becoming cosmic strings with mass densities of over 100 million tons per centimeter. That's the weight of a mountain range compressed into a filament thinner than a quantum particle. Unlike black holes, they don't form from collapsing stars. They're primordial scars woven into the structure of reality itself. A close encounter with one would be unlike any other cosmic catastrophe. Because strings warp space-time itself, their gravitational effects are bizarre. They wouldn't pull objects inward like a black hole. Instead, they'd create what physicists call a conical singularity, distorting space so that if you circled a string, you'd end up with less than 360 degrees in your path, like cutting a slice from a pie and taping the edges back together. Light passing near one would bend into double images, creating ghostly duplicates of stars. If a string drifted through our solar system, planets might suddenly find their orbits shifted by degrees, their paths subtly rewritten by the invisible scissor cutting through space-time. The most unsettling property, cosmic strings could be vibrating. Some models suggest they might oscillate at relativistic speeds, whipping through galaxies like invisible bullwhips. These vibrations could emit gravitational waves powerful enough to be detected across the universe, or, if close enough, shake apart star systems. In the 1980s, astronomers studying distant quasars noticed strange, repeating patterns in their light that some theorized could be the fingerprint of a cosmic string lensing light as it passed. While later observations ruled out that particular case, the hunt for these space-time cracks continues. Yet for all their destructive potential, cosmic strings might also hold the key to cosmic mysteries. If detected, they'd offer direct evidence for grand unified theories of physics, revealing insights about the universe's first trillionth of a second. Some even speculate advanced civilizations might harness strings as power sources or cosmic-scale instruments, though the engineering challenges would dwarf anything humanity has attempted. For now, these filaments remain both tantalizing and terrifying, a reminder that the universe's earliest moments might have left behind traps we can't yet see, waiting to rewrite reality with a single, infinitesimal cut. Whether they're out there or not, cosmic strings challenge our understanding of existence itself, proving that the universe's most dangerous objects aren't always the ones we can spot from light years away. Sometimes the deadliest threats are the ones hiding in the equations. Deep in the void between constellations Centaurus and Hydra, something unseen tugs at our galaxy with irresistible force. An invisible hand guiding the Milky Way's motion through the cosmos at 14 million miles per hour. Astronomers call this phantom the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxy clusters toward it like moths to a flame. Yet despite decades of searching, we still don't know what lurks at the heart of this cosmic mystery. Is it simply a supercluster of galaxies we can't see clearly, or something far more bizarre warping space-time itself? Our first clue came in the 1970s when astronomers mapping cosmic microwave background radiation noticed something odd. The Milky Way wasn't drifting randomly. Something colossal was pulling us, along with the entire local group of galaxies, toward a point roughly 250 million light-years away. The sheer scale of this motion defied explanation. To move galaxies like chess pieces would require the mass equivalent of tens of thousands of Milky Ways crammed into one region. Yet when telescopes scanned the suspected area, they found only scattered galaxies, nowhere near enough to account for the gravitational pull. The mystery deepened when astronomers realized the Great Attractor lies directly behind the Milky Way's crowded central plane, a region called the Zone of Avoidance where dust and stars block our view. It's like trying to spot a lighthouse through a sandstorm. Only with X-ray telescopes like NASA Chandra and infrared observatories could scientists peer through the cosmic fog. What they found was shocking. Behind the galactic smokescreen lurked the Norma cluster, a dense knot of galaxies with a combined mass of 1 quadrillion suns. But here's the twist: even this gargantuan structure only explains part of the pull. There's something heavier behind it, something we still can't see. Some theorists propose an unsettling possibility: the Great Attractor might not be the final destination. Our galaxy's trajectory suggests we're being pulled towards something even more massive beyond it, possibly part of the Shapley supercluster, the largest known structure in the observable universe. Others speculate about exotic physics at play: cosmic strings warping local space-time, or even a concentration of dark matter so dense it functions like a gravitational anchor for this corner of the universe. The most chilling hypothesis: the Great Attractor could be a focal point for something much larger, a vast flow of galaxies all marching toward the same cosmic convergence, like rivers draining into an ocean we can't yet perceive. Astronomers call this the dark flow, a mysterious large-scale motion that suggests structures beyond the observable universe's horizon might be tugging at everything we see. Yet amid these speculations lies a profound realization: we're not just passive observers of the cosmos. The Milky Way is caught in this relentless current, riding gravity's conveyor belt toward an unseen destiny. Every second, we travel another 400 miles closer to whatever waits in that darkness. Whether it's a supercluster, a flaw in space-time, or something beyond our current physics, one thing's certain: the universe still holds giants in its shadows, and they're pulling us toward answers we're not yet ready to understand. Wolf-Rayet stars are the universe's ticking time bombs, cosmic behemoths so unstable they're literally tearing themselves apart in a blaze of radioactive fury. Imagine a star 20 times more massive than our Sun, burning at temperatures over 200,000 degrees Fahrenheit, and shedding its own atmosphere into space at speeds exceeding 6 million miles per hour. These aren't just stars living out their lives, they're stellar suicide bombers, detonating layer by layer in a slow-motion explosion that lights up entire galaxies. And if one existed in our cosmic backyard, its death throes could render nearby solar systems uninhabitable long before the final supernova. Take WR-104, a notorious Wolf-Rayet star in the constellation Sagittarius. Through telescopes, it looks more like a celestial hurricane than a stable ball of plasma. Its surface roils with turbulence, ejecting solar masses worth of material in violent outbursts that form glowing nebulas around it. The star's stellar winds particles, accelerated to near light speed, carry enough energy to strip atmospheres from planets light-years away. In fact, WR-104 is surrounded by a pinwheel of ejected gas, a spiral pattern carved by its own rotation as it flings matter into the void like a spinning fire hose. The true danger lies in what these stars leave behind. Wolf-Rayet stars are the precursors to some of the most violent supernovae in existence, including rare type Ike hypernova. Unlike typical supernova, these explosions lack hydrogen and helium in their spectra because the star has already shed those layers. What remains is a dense core of heavy elements like carbon and oxygen, primed to detonate with 10 times the energy of a normal supernova. When one goes off, it doesn't just shine brightly, it fires relativistic jets of gamma rays and cosmic rays capable of sterilizing planets across entire galactic arms. But the horror doesn't stop at the explosion. Wolf-rayet stars also seed their surroundings with radioactive isotopes like aluminum-26 and iron-60. These elements emit gamma rays as they decay, bathing nearby star systems in a slow, insidious radiation bath. Astronomers have found traces of these isotopes in meteorites, evidence that Earth was likely sprinkled with debris from a nearby Wolf-rayet death millions of years ago. If a star like WR-104 were within a few hundred light-years today, its decaying isotopes could trigger global mutations, cancer spikes, and ecosystem collapses, a silent apocalypse unfolding over millennia. What makes these stars especially terrifying is their unpredictability. Unlike red giants which expand predictably before dying, Wolf-rayet stars are chaotic. Some erupt in sporadic mini-supernova, called luminous blue variable eruptions, temporarily outshining their host galaxies. Others collapse directly into black holes without warning, their cores imploding under their own weight in seconds. The only consolation, they're rare. The Milky Way hosts fewer than 200 known Wolf-rayet stars, most concentrated in violent star-forming regions like the Carina Nebula. Yet for all their destructive potential, these stars are also cosmic alchemists. Their furious winds enrich the interstellar medium with heavy elements crucial for rocky planets and life itself. The carbon in your DNA, the oxygen in your lungs, even the iron in your blood were likely forged in a Wolf-rayet star's furnace before being blasted into space by its explosive death. They're the universe's way of recycling destruction into creation, proving once again that the most fearsome forces in space often hold the keys to existence. So while we're lucky none are close enough to threaten Earth today, we owe our very atoms to their cataclysmic lives and deaths. Thorn-Zitkow objects are the universe's most bizarre stellar hybrids, red supergiants with a neutron star beating at their core like a cosmic parasite. Picture a star so massive it could swallow our solar system whole, yet hiding a city-sized corpse in its heart, spinning silently beneath layers of churning plasma. These aren't just theoretical oddities, they're ticking time bombs, they're unstable fusion processes capable of detonating in ways that defy conventional stellar physics. And if one erupted nearby, the fallout would make a supernova look like a firecracker. The formation of these monsters reads like a cosmic horror story. When a neutron star itself, the remnant of a supernova, gets caught in the gravitational embrace of a massive red supergiant, it doesn't just orbit. It spirals inward over millennia, dragged down by friction until it plunges into the star's core. There, the neutron star's unimaginable density reshapes the entire star's nuclear reactions, creating a bizarre mix of processes unseen anywhere else in nature. Hydrogen fuses into heavy elements not in the star's core, but around the neutron star's surface, producing exotic isotopes like rubidium, lithium, and molybdenum in quantities that would be impossible under normal stellar conditions. What makes Thorn-Zitkow objects especially terrifying is their volatility. Unlike typical red supergiants which die in predictable supernova, these hybrids are wild cards. Some might collapse silently into black holes, the neutron star at their core swallowing the surrounding star whole. Others could erupt in hyperviolent explosions, their unusual fusion processes triggering asymmetrical detonations that fling stellar debris at relativistic speeds. In one hypothetical scenario, the neutron star's magnetic field, already trillions of times stronger than Earth's, could become entangled with the star's plasma, launching jets of radioactive material across interstellar space like galactic shrapnel. The debris from such an explosion would be unlike anything produced by ordinary supernova. Instead of mostly iron and silicon, the ejector would be laced with rare, neutron-rich elements forged in the hybrid's unique environment. These isotopes could decay into gamma-ray emitting particles, creating long-lived radiation zones around the explosion site, deadly hotspots for any passing solar systems. A Thorne-Zitkow object going off within a few hundred light-years might not sterilize planets outright, but the lingering fallout could poison star-forming regions for millennia, altering the chemistry of future worlds. Detecting these objects is a challenge that borders on cosmic hide-and-seek. Only one strong candidate has ever been found, HV 2001-12 in the Small Magellanic Cloud, and even its classification remains debated. Thorne-Zitkow objects masquerade as normal red supergiants until close inspection reveals their abnormal chemical signatures. Their predicted lithium and rubidium overabundances are like cosmic fingerprints, but with most lurking in dense star-forming regions obscured by dust, we might be surrounded by invisible time bombs without knowing it. Yet for all their destructive potential, these stellar oddities could hold keys to unlocking cosmic mysteries. Their unique nucleosynthesis might explain the origins of rare elements in our own solar system, while their extreme environments could test theories of quantum physics under conditions no lab could replicate. Some researchers even speculate that advanced civilizations might harvest them as natural particle accelerators, tapping into their neutron-rich debris for technology beyond our imagination. The universe has a way of hiding its most dangerous creations in plain sight. Thorne-Zitkow objects remind us that even the familiar, a twinkling red giant in the night sky, might harbor something unimaginable beneath its surface, waiting to rewrite the rules of stellar life and death. Whether they're cosmic curiosities or existential threats depends entirely on where and when they decide to reveal their true nature. Dark energy is the universe's silent saboteur, an invisible force lurking in the emptiness of space, pushing galaxies apart faster than gravity can hold them together. Imagine a cosmic tug-of-war where one side keeps getting stronger, its grip relentless until eventually even the fabric of reality starts to fray. This isn't just theoretical doom-mongering. The evidence is etched in the light of distant supernova, their glow stretched redder and dimmer than it should be, revealing a universe expanding at an ever-increasing pace. And if this acceleration doesn't stop, the end game could be something far worse than a slow fade into darkness. It might be the violent, all-consuming Big Rip. Picture this scenario: trillions of years from now, the repulsive force of dark energy grows so dominant that it overpowers every other force in nature. First, galaxy clusters bound by gravity for billions of years begin to drift apart, their stars scattering like dust in a hurricane. Next, the galaxies themselves unravel. The Milky Way's spiral arms stretch and snap, stars flung into the void as dark energy's grip tightens. But the horror doesn't stop there. As the expansion accelerates further, even individual star systems aren't safe. Planets are ripped from their orbits, moons from their planets, until eventually, the very atoms holding matter together can't withstand the strain. Electrons are torn from their nuclei, protons and neutrons shredded into quarks. A cosmic disintegration so total, it reduces existence to a soup of disconnected particles, forever drifting in an infinite, empty void. What makes dark energy so unsettling is its sheer mystery. We know it exists because of its effects, but we don't know what it is. Some theories suggest it's a property of space itself, Einstein's cosmological constant come to life. Others propose it's a dynamic field, like an anti-gravity fluid permeating the cosmos. The most chilling possibility: dark energy isn't constant at all. It could be growing stronger over time, its density increasing as space expands, setting the stage for the Big Rip long before stars have even burned out. The timeline for this apocalypse depends entirely on dark energy's behavior. If it's truly constant, the Big Rip might never happen. Just a slow, cold death as galaxies vanish over the horizon of observable space. But if it's phantom dark energy, a more aggressive variant that strengthens with expansion, the end could come shockingly soon by cosmic standards, in as little as 22 billion years. That might sound distant, but remember, the universe is already 13.8 billion years old. We could be closer to the end than we are to the beginning. Yet amidst the doom, dark energy also holds clues to the universe's deepest secrets. Its discovery in the 1990s upended cosmology, proving that the universe wasn't just expanding but accelerating, a revelation so unexpected it earned its discoverers the Nobel Prize. Understanding dark energy might finally reconcile quantum mechanics with general relativity, or reveal hidden dimensions folded into spacetime. Some theorists even suggest it could be the key to manipulating gravity itself, unlocking technologies like artificial wormholes or warp drives. For now, though, dark energy remains the ultimate wildcard, a reminder that the universe isn't just expanding, but doing so with a force we can't see, can't touch, and barely understand. Whether it leads to a slow fade or a violent tear, one thing's certain: the cosmos has a way of humbling us, revealing that even the emptiest corners of space hold the power to rewrite existence itself. So the next time you look up at the night sky, remember, those distant galaxies aren't just drifting away. They're running for their lives. Primordial black holes are the universe's forgotten ghosts, leftovers from the Big Bang's chaotic first moments, when density fluctuations in the newborn cosmos collapsed directly into tiny, ravenous singularities. Unlike the black holes we know today, forged in the depths of massive stars, these ancient relics could be as small as an atom yet pack the mass of a mountain. And if they exist, some might still be drifting unseen through our solar system, their gravitational whispers tugging at comets and planets while they slowly, violently evaporate into nothingness. Imagine an object so dense, a single teaspoon of it would outweigh Mount Everest. Now picture that object cloaked in darkness, invisible to telescopes, yet bending light around it like a cosmic mirage. That's the eerie reality of primordial black holes. Born in the extreme pressures of the early universe, they've had billions of years to wander, some possibly captured by the gravity of galaxies, or even our own sun. A primordial black hole the size of a grapefruit could orbit silently beyond Neptune, its presence betrayed only by the occasional flicker of a star as it passes between us and distant starlight, or the unexplained perturbation of a spacecraft's trajectory. What makes these objects especially unsettling is their volatility. Thanks to Hawking radiation, a process where black holes lose mass by emitting quantum particles, smaller primordial black holes wouldn't last forever. A black hole with the mass of an asteroid would emit radiation so intense, it would glow with the heat of a nuclear blast, evaporating completely in a final, explosive burst of gamma rays. If one were lurking near Earth, its death throes could unleash a radiation storm capable of sterilizing the planet. Yet the true danger isn't just their explosive end, it's their gravitational chaos. Even a black hole no larger than a pinhead could wreak havoc as it passes through matter. Drifting through Earth, it wouldn't just tunnel cleanly. Its immense gravity would generate seismic shockwaves, heating the interior as friction with surrounding rock releases energy comparable to volcanic eruptions. Oceans might boil at the point of entry, tectonic plates could fracture, and the resulting earthquakes would dwarf anything in recorded history. Some theories suggest primordial black holes could explain dark matter, their collective gravity binding galaxies together without emitting light. Others propose they're the seeds of supermassive black holes, growing over eons by swallowing stars and gas. But the most tantalizing and terrifying possibility is that they're out there right now, hidden in the frozen dark of the Oort cloud or the shadowy reaches of the asteroid belt, ticking away like cosmic time bombs. Whether they're relics of creation or phantom killers, primordial black holes force us to confront an uncomfortable truth. The universe's deadliest objects might not be the ones we can see, but the ones we've overlooked. And if one day a star flickers strangely or a planet's orbit shifts without explanation, we might realize too late that we're not alone in the solar system. We're sharing it with remnants of the Big Bang itself. Rising from the heart of the Milky Way like twin ghosts, the Fermi bubbles stretch 25,000 light-years into space, cosmic hot air balloons glowing with gamma rays, their origins rooted in ancient violence we're only beginning to understand. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these colossal structures aren't just remnants of some forgotten cataclysm. They're evidence that our galaxy's quiet center can awaken with eruptions powerful enough to reshape interstellar space. If such an event happened today, the fallout could bathe Earth in radiation capable of rewriting the destiny of life itself. Imagine the scale. Each bubble dwarfs our entire solar system, their surfaces shimmering with high-energy particles accelerated to near light speed. The leading theory suggests they were forged by a titanic outburst from Sagittarius, a star, the supermassive black hole at our galaxy's core, roughly 2 to 4 million years ago. Picture the black hole devouring a gas cloud or star so voraciously, it belched out jets of plasma and radiation with the energy of 100,000 supernovae. Those jets punched through the galactic disk, inflating the bubbles like cosmic blowtorches, while their shockwaves accelerated particles to energies that still glow faintly in gamma rays today. But here's what keeps astronomers awake at night. The Fermi bubbles aren't just relics. They're proof that our galactic center is capable of Chinese letter violence. Sagittarius, a star, might seem dormant now, but infrared observations reveal it flared dramatically as recently as the 14th century. A flicker compared to the bubble's creation event, yet a reminder that the monster can stir without warning. A full-scale eruption today would unleash a double-barreled catastrophe. First, a barrage of gamma rays and X-rays would ionize Earth's upper atmosphere, crippling satellites and frying power grids with continent-sized EMPs. Next, the shockwave's particles would arrive months or years later, a slow drip poison of cosmic rays increasing cancer rates and mutating ecosystems over generations. The most unsettling part, we'd have no time to react. Light from the eruption would reach us at the same moment as the deadly radiation. One moment, telescopes would see Sagittarius, a star, brightening like a cosmic flare. The next, our atmosphere would light up with auroras visible at noon as it absorbed the blast. Ancient ice cores hint this might have happened before spikes in radioactive isotopes like iron-60 suggest Earth was dusted with fallout from a nearby galactic explosion roughly 2.5 million years ago, around the time the Fermi bubbles likely formed. Yet these structures aren't just omen-laden ruins, they're also cosmic laboratories. The bubble's edges act as particle accelerators far more powerful than anything on Earth, revealing how black holes funnel energy across galactic scales. Their gamma-ray glow helps astronomers map the Milky Way's magnetic fields, invisible scaffolding that shapes star formation. And buried in their spectra might be clues to dark matter, as some theories suggest the bubble's particle haze could include annihilation products from these elusive particles. The Fermi bubbles force us to confront a humbling truth. We live in the aftermath of a galactic-scale temper tantrum, one that could repeat at any time. They loom above us like silent sentinels, a reminder that the universe doesn't need malevolence to threaten life, just the indifferent physics of a black hole's past or future indigestion. Whether they're tombstones for lost worlds or signposts to deeper cosmic mysteries, one thing's certain: their discovery rewrote our understanding of home. The Milky Way isn't just a quiet spiral, it's a sleeping dragon with scars to prove it. From black holes that shred spacetime to gamma-ray bursts capable of sterilizing galaxies, we've journeyed through the cosmos's darkest corners where danger wears many faces. These 25 celestial horrors aren't just theoretical, they're reminders that Earth floats in a shooting gallery of unimaginable forces. Our planet, a pale blue dot in the void, survives not through armor but by cosmic luck. A rogue black hole could drift unseen into our solar system tomorrow. A magnetar's flare might already be racing toward us at light speed, its deadly radiation undetectable until it strikes. Even the vacuum of space itself could betray us, collapsing into a lower energy state without warning, rewriting the laws of physics in an instant. Yet this fragility is also what makes existence precious. Every sunrise, every breath, is a statistical miracle in a universe where stars explode, galaxies collide, and invisible giants like dark energy stretch reality itself to its breaking point. The same violence that threatens us also forged the iron in our blood and the calcium in our bones, remnants of long-dead stars that burned bright before scattering their guts across the cosmos. We're the universe's way of understanding itself, fleeting and fragile, but alive in a sea of chaos. So what do we do with this knowledge? We watch the skies, not with fear, but with resolve. Humanity's greatest defense isn't hiding its learning. Every telescope pointed at a quasar, every probe sent to study asteroids, every equation unraveling dark matter brings us closer to predicting or even preventing cosmic disasters. One day, we might deflect asteroids, harness antimatter, or outrun a dying star. Until then, we keep exploring because survival favors the curious. Look up tonight. Those stars aren't just lights, they're warnings and wonders, destroyers and creators. In their glow, we find our place, small, yes, but eyes wide open in the dark. The universe may be indifferent, but we don't have to be. Our greatest weapon against the void isn't strength, it's paying attention.